All right, so what does all this lead to? I mean, what are some practical or observational results? So now we're going to talk about how energy is quantized, and I'll explain that in a minute or so, okay? So this is a famous model. Whenever you learn quantum physics, you always talk about this model. So it's called a particle in a box model. And we're going to learn, like I said, we're going to learn about quantized energy, okay? So, this is like the particle cannot escape, all right? So just think of it as, 3 feet of steel or something like that, all right? So a classical particle bounces back and forth. You can't escape, okay? Great. And so if classically the speed can be anything, right? There's no limit. And therefore the energy can be anything, right? No problem. However, if the particle acts like a wave and is bouncing back and forth and it's confined, that's an important word, if it's confined to the box, that means that the waves have to reflect back and forth, right? All right, so we're talking about matter waves. That's woohoo, right? Matter waves travel in both directions. Okay? Now, what kind of wave is that? We studied it in gory detail some time ago. What kind of wave is that when it just goes back and forth, back and forth, back and forth? A standing wave, right? A standing wave. All right, so the reflected wave creates a standing wave. So we're thinking of the particle as a wave. It's going back and forth, right? So it just keeps reflecting back and forth. Now, what does that remind you of? Where have you seen that before? Remember we talked about air columns, sound waves and air columns? Remember that? So that's a closed air column, right? And you can see that the displacement, right? No oscillations, a node, right? Antinode, node, and so forth and so on, All right, so let's talk about this. Let's see what we get. We're going to use the same analysis that we used when we talked about sound waves. That's why we did it, believe it or not, so we can use it now. Okay, so we're just looking at the blue, right? The blue waves, the displacement waves, okay? All right, so the air column is L. That's the length L. So you can see that this is a half a wavelength. This is 1 wavelength. This is 1.5 wavelengths, right? So, okay, so L is lambda over 2, 2 lambda over 2, 3 lambda over 2, and so forth, right? We did this before. So basically we're just going to say, therefore, we're just going to say L, the length of the air column, is N lambda over 2, right? Where N is just it's an index. Remember the index? 1, 2, 3, on and on and on. All right? So therefore, let's solve for lambda. So lambda equals 2L over N. Let's put a little n here, because the wavelength depends on the n, right, the index. All right, but what did de Broglie say? De Broglie said lambda equals h over p, which is h over mv. That's the de Broglie relationship, right? Okay, so let's put them together. So we're going to have, therefore, we're going to have 2L over n equals h over mv. Okay, solve for the velocity. Solve for the velocity. So therefore, the velocity equals nh over 2ml, right? And we can, remember, n is an index, so we kind of want to pull it outside. So that's equal to n times h over 2ml. All right, so that's a velocity. Okay, sorry, got to erase. All right, so now, come on. We have the velocity. Well, what kind of energy does this thing have, this particle in the box? It has, it has kinetic energy, right? Let's solve for the kinetic energy. So the kinetic energy is 1/2 mv squared, So E, and put a little n there, right? Put a little n there. So En 1/2 mvn squared. Put a little n there, makes it happy, right? Okay? So we have 1/2 m. Now we're going to square that thing. So we have n squared h squared over 4 m squared L squared. Okay, well, 2 times 4 is 8, and this mass kills that mass, so get rid of that, get rid of that, get rid of that, make that an 8. And there you go, all right? So the energy of the particle is n squared times h squared over 8mL squared. Now look at, what's this? Well, that's just E1, right? I mean, right? You know, E1 is 1 times this, so this is just E1. So I can basically just say that En equals n squared. It's an n, not an h. N squared times E1. Now, this is not a math class, right? This is incredibly important. What does it mean? What does it mean? Again, classically, you know, you put a particle in a box, you can have any speed you want. You can have any energy you want. In quantum mechanics, because the particle acts like a wave, what does this say? You can only have certain energies, right? You can only have certain energies. And this is insane, you know, when you think about classical physics. I mean, here's an analogy. So I used to run track a long time ago. So let's say you're running, let's say you have a workout. You're doing 400-meter sprints, right? 1 lap around the track. So let's say, you know, let's say the coach says, you know, do them in 60 seconds, all right? Do each 400-meter sprint in 60 seconds, then rest 200 meters or whatever, you know? Okay, so that's what you're supposed to do. Let's say the first one you get all excited, you do 58 seconds, then you do a 57, then you do a 59, then you're tired, so you do a 60. But basically, I mean, if you want to, you know, you can do a 58.5, right? You can do a 57.2. You can do whatever you want to do, as long as you're in shape, and, you know, and you've had a motivation. But you can do whatever you want to do. According to this, what this says is, sorry, this says, I'm just analogy, right? This says you can only do a 65, and a 70, and a 60, and a 75. You can't do anything in between. I don't care how hard you try. It's impossible for you to do like a 63 or a 62 or 70.5 or something like that. So that's what we mean. Energy is quantized. There's only certain values of the energy. This is completely nuts according to classical physics, right? But this is how quantum physics works. The electron can only, or the particle, sorry, the particle can only have certain values of the energy. That's life. That's how it is. Okay? So crazy. So what's this like quantization? That means it comes in pieces. It's kind of like this. Let's say you go to Foodland and you go to the worker and you say, I'd like to buy a half an egg, please. Well, what's the person going to do? What, are you crazy? You can't buy a half an egg, right? Because eggs are quantized. They come in units. Or like you go to the bank. I'd like a half a penny, please. What, are you nuts? You can't get a half a penny. Well, this is what it says. The particle in a box, you can only have certain values of the energy, period. That's kind of how it is. It's weird, right? Okay, now, let's go back. What led to this whole business, you know, of having energy quantized? It was the fact that the particle was confined, right? The particle could not escape the box. So it had to have a node here and a node here, and had to make the standing wave, right? So that's why we have quantized energy. The particle was confined to the one-dimensional box. Well, now what I want you to think about, think of an atom. Oops, sorry. Forgot to show you that, all right? Quantized energy, right? Eggs, you know, money, all right. Okay, so get back to what I was saying. Think of something that's confined. Here's an atom, right? Here's an atom. Are the electrons confined? We're just talking about, you know, we're not talking about, you know, heating up the atom or shooting ultraviolet light at it. Just a regular, ordinary atom, just sitting there by itself, minding its own business, okay? Are the electrons confined to the atom? Yes, they are. Okay, so if the electrons are confined to the atom, what does that imply about their energies? They're going to be quantized, okay? They're going to be quantized. All right? So, now let's discuss that. Kind of in gory detail, all right? Let's discuss this. All right, so this is just classical physics, right? If you shine light through a prism, different light is refracted depending on the wavelength of light, right? And so the different colors means different wavelengths. Remember that from a long time ago? Okay, so different colors, different wavelengths, and the refraction angle depends on the wavelength. Okay, so we all know this is nothing. And this is called the spectrum, right? When you know, spectrum means different wavelengths, different, okay. All right, different frequencies and all that. Spectrum of light. Okay, so we know all that. All right, here's what's cool. Okay, so we want to do an experiment. A couple of them, 3 of them. So this is a prism. Here's light, and the light hits the prism. And the prism, you know, here, you can say the prism is like a diffraction grating in a spectrograph. All right, don't worry about it. All I'm saying is the prism, you know, it's going to split up the light into its different wavelengths, okay? Just like a diffraction grating does. In astronomy, astronomers do this all the time. They split up the light into its different wavelengths, and they use something called a spectrograph, all right? So this could be either a light bulb or a star, but whatever, we don't care. Okay, so the light hits the prism or the spectrograph, and as I just said, what happens? The light bulb produces a smooth, continuous spectrum of thermal radiation, right? So that is supposed to be that, okay? So there's nothing between the star or the light bulb and the spectrograph or the prism, right? So it just splits it up into this nice continuous band, you know, where the light changes wavelength, changes color, right? Smooth, so here's the intensity. You see it's a smooth, continuous spectrum, right? I don't care about the thermal rate, I don't care about the name, don't worry about that. All right, so that's cool. I mean, you know, everybody knows about that. You know, people have these prisms on outside their house and the sunlight hits it and you get this beautiful prism on, you know, whatever. All right, now let's change it a bit. Now we're going to concentrate on here. So here's a light bulb or a star, and here's a thin cloud of gas, right? And so now we're looking at the light through the cloud of gas, right? So let's read it. If we view the light bulb through a cloud of gas in front of it, the spectrum shows dark absorption lines where specific colors of light are missing from the rainbow. So see that? So you're looking at the light bulb through the gas, and look what happens. Instead of seeing this nice continuous thing, you see places where the light is being absorbed, right? See these dark lines? So the light, for whatever reason, at certain wavelengths only, is getting absorbed by the cloud. Now why? And why only certain frequencies or certain wavelengths, you know? Well, we'll get to it, all right? Okay, so that was a big mystery in the olden days. Okay, now what we want to do, we want to just look through we're going to look just at the cloud. So in other words, we don't see the light bulb. It's way off to the side, right? We're just looking at the cloud. So we should expect to see nothing, right? Because, you know, we don't see the light. We don't see the light bulb or the star. We're just looking at the, you know, the cloud. Darkness, you know? So you'd expect to see nothing, black. Well, so much so for expectations. If we view the gas cloud from the side, we see only the light emitted by the gas itself. What? So the gas is emitting light. All right, that's all right. This spectrum consists of bright emission lines of specific colors against a black background. So for whatever reason, the cloud is emitting light. Only at certain wavelengths though, right? So it's dark, except for these certain wavelengths, it's bright. Okay, so people were totally confused about that. Now it gets even weirder. Here's something that's weird too, right? Look at where you have a dark line here, right? When you're looking through the cloud at the light, you get a bright light here when you're looking just at the cloud. You know, whenever you see a pattern in nature, Mother Nature wants to tell you something's going on, right? I mean, you know, you should be able to explain all patterns. So So at the same wavelength where the light was absorbed here, the light's being emitted here. Whoa, like, is that a clue or what? You know? All right, here's another one. Okay, so what happens here, you take the element and you heat it up and it emits light. And every element has a unique spectrum. So this one is barium. So every barium atom in the universe, you know, if you heat it up and you got it to emit light, it would emit light at these specific wavelengths. It's all kind of like a fingerprint, right? You know, this is calcium, hydrogen, sodium, right? So only specific wavelengths, though. Why not other ones? So people were clueless. Okay. All right, so this is, remember, this is like the classical atom, right, that you probably learned in high school or junior high school or something like that. You know, you have the nucleus and the electrons zip around, you know. So that model is completely unable to describe these lines, okay, completely clueless, all right? Not only is it clueless about explaining those lines, it can't even explain how come atoms are stable. We learned something when we talked about electricity and magnetism. We said that whenever you have an accelerating charged object, it emits light, right? Well, therefore, it loses energy. So if you have these electrons orbiting the nucleus, they're accelerating, they're going in a circle, so they're emitting light, and therefore they're losing energy. If they lose energy in a very short amount of time, they should be crashing into the nucleus. So if you work it out, an atom shouldn't live more than like a millionth of a second or something. I don't remember exactly, but okay. So this model can't explain the spectral lines, and it predicts that the atoms should be self-destructing. Great model, right? All right. So what are we going to do? We got to use quantum physics. We got to use quantum physics. So let's do it. So this is just, yeah. So this is what quantum physics says. So quantum physics says that that an atom can only exist in certain stationary states. Okay, there's only certain states that an atom can exist in, and every stationary state has an associated energy. Okay, so this is called the energy diagram for hydrogen. So quantum physics says a hydrogen atom can be in this state, have this energy, and that's like the n equals 1, right? Remember the index? Or it can exist in this state with this energy, or it can exist in this state with this energy, but it's impossible for the hydrogen atom to have an energy between minus 3.4 electron volts and minus 13.6. In other words, you're never going to get a hydrogen atom with like minus 10, because the energy is quantized, all right? These are the only states you can have a hydrogen atom exist in. You will never find a hydrogen atom with any other energy. I kind of like this. Just as I can't stand between two adjacent steps, an electron can't exist between two energy levels. All right, that's cool, right? Okay. Now, how can an electron, or how can a hydrogen atom, go from one state to another state? Like, how can it go from a low energy state to a higher energy state, or vice versa? How does it do it? Because, you know, it can exist in all of these different energy levels, right? So how does that happen? All right, so an atom can jump from one stationary state to another stationary state by either emitting a photon or absorbing a photon. All right, now it's not any old photon, okay? So here, so the energy of the photon, which again is HF, right? That has to be the change in energy levels. So what am I talking about? So here, so in other words, if a hydrogen atom goes between here and here, there's a change in energy, right? And the photon that's absorbed or emitted, depending if it's going here to here, has to be exactly equal to that energy difference. Let me give you some examples. Okay, so here's a hydrogen atom, right? Here's the nucleus, the proton, and here's the electron. This is called the ground state, the n equals 1. So this is not the ground state, so it's called an excited state, right? So here you have this hydrogen atom. The electron is in a higher excited state, all right? Now, let's say, I'm sorry, this is the ground state. Yeah, I said that. This is excited state. Okay, now just like people, people don't want to stay excited very long, right? They want to be couch potatoes, after a hard day at work, right? Okay, so hydrogen atoms, like any other atom, they usually reside in their couch potato state, their ground state. All right, so here you have this excited electron. What's going to happen? What's going to have to happen for this guy to go down to its ground state? Well, this is a high energy state. This is a low energy state. So in order to go from a high energy state to a low energy state, what are you going to do? You get rid of some energy. How are you going to do that? By emitting a photon. Okay? The energy of this photon is exactly equal to the energy difference between this state and this state. So the electron jumps to a lower energy state and emits a photon. Okay, let's do the other one. Here's a couch potato electron, right, in the n equals 1 ground state. Here you have an approaching photon. If this photon has exactly the amount of energy between this state and this state, what's going to happen? The electron's going to absorb it and it's going to jump. So the electron absorbs the photon and jumps to a higher energy stationary state. So that's how it happens. Let's do some numbers. What do you say? Okay, so all right. So here's the ground state, n equals 1. Here's n equals 2. Here's n equals 3. Right. So here's all the energies. Right. Here's all the energies. Okay. So let's say the electron is in the 3 state. So it's in a 3 state, and it wants to go to the 2 state because it's right lazy bum. Right. We want to go from a higher energy state to a less energy state. So this is from 3 to 2. Okay. Well, what's the difference in this? 1.9, right? Right? The difference between this is 1.9 eV. So that means that this photon has to get rid of 1.9 eV. And it does. Right? So this photon gets rid of 1.9 electron volts. That's called emission. Let's do absorption. So now the electron's in the 2 state, wants to go to the 3 or whatever. Doesn't want to, but it's going to, right? And so again, the difference in the 2 and the 3 is 1.9, all right? So how is it going to get enough energy to go from the 2 to the 3? Well, it's going to absorb that photon with 1.9 electron volts. Therefore, it will have exactly the right energy to go to the 3 state. Nothing else will work. It has to be exactly those energies. So what am I saying? So every element has a unique energy diagram, right? Everybody's going to have different numbers, for all the energy levels. So what I'm saying is that, only certain wavelengths, only certain energy photons are going to allow it to go from state to state, right? The absorption or the emission, only certain energies. Well, don't forget, for a photon, E equals hf, which is hc over lambda. So if there's only certain wavelengths, only certain energies, that means only certain frequencies, only certain wavelengths. And so therefore, when you look at the absorption lines and the spectrum lines, what do you see? Only certain wavelengths are absorbed, only certain wavelengths are emitted. That exactly agrees with what we've been talking about. And like I said, look at here, outgoing between 2 and 3, 1.9. Incoming between 2 and 3, 1.9. So how should these wavelengths match up? They should match up exactly, right? And they do, all right? So there you go. So quantum physics explains all this stuff, which people were so clueless about for such a long time. Okay. All right, so quantum physics says stationary states, quantized energy. The energy of a photon is hf, and that's the difference between energy levels, right? So atoms emit and absorb a discrete spectrum. That means, discrete means just certain wavelengths, right? It's not continuous, it's discrete, certain wavelengths only. Absorption wavelengths are a subset of the wavelengths in the emission spectrum, right? Same wavelengths. Okay. And then, of course, each element has a unique spectrum, right? And that's because of that's because every element has a unique energy level diagram with, with unique energy values for each state. Okay, so every element has a unique spectrum. And again, atoms naturally seek the n=1 ground state. I call it the couch potato state. And so most of the atoms in nature are usually found in the n=1 state. And that is a good place to quit. All right, good.